I'll be okay. All right. So today we are going to learn about first derivative and second derivative tests and what they can do for us in terms of learning about a curve. Um, and the first thing they tell us is that a function is increasing or decreasing. Now, here's my function right here. You tell me, is the function increasing or decreasing? Increasing or decreasing? Neither, right? So here's what we say. We say that if you were to draw the derivative at any of these spots, and if the derivative is positive, then the function is increasing. So as I draw a bunch of derivatives here, you see that wherever the derivative is positive, the function is increasing. Wherever the derivative is negative, the function is decreasing. So increasing, f prime of x is greater than 0. I cannot overstate how important it is to try to internalize and memorize everything I write on this upper part up here. You will use it for the rest of the year. Decreasing is where f prime of x is less than 0. A local max or a local min will happen in this situation. Okay? If I look at the local max right here, notice that as I move from left to right, what happens with the derivative as I move left to right? It goes from positive to negative. You see that? So the max will be where f prime of x, and I'll write it like this, changes from positive to negative. It's got to change sign. Do you notice that at that spot, the derivative is equal to 0? Okay? But just because the derivative is 0 doesn't mean it's a local max or min. Let me give you the example. If I have a function that looks like this, if I take the derivative right here, I get 0, correct? And it is a local min. But if I look at this function right here, if I take the derivative at this spot, I get 0. But is it a local max or min? No. The derivative was positive, then 0, then positive. It never changed from positive to negative or negative to positive. You got to see change in the derivative value. So if we want to see a local min, notice what happens. We'll pick up with Katie's logic. As I have a local minimum here, what happens to the derivative? It changes from negative to positive. Again, that's something you need to internalize. You got to be able to really think that through and convince yourself of it. F prime of x changes from negative to positive. Is everybody okay with those first few ideas? Then what does the second derivative test tell us? Okay, and that's really, really a lot more complicated for people to think through. I'm going to erase this, and I'm going to try to do my best to help you understand what the heck is happening with the second derivative. The second derivative is the rate of change of the first derivative. Okay? That's not supposed to just all of a sudden click for you. We got to kind of, chew on that for a while. Okay? It's like a tough piece of steak. After a while, it'll be all right. Ooh. It's like okay, if you don't like steak, it's like chewing a tough piece of asparagus. Yeah, you overcook it. I don't know. Isn't it kind of gummy? I hate it. All right, so these blue lines represent the derivative of the function at all sorts of spots, okay? Now, the derivative, positive or negative? Positive. More positive or less positive? Less positive. So if you could tell me over this little stretch here, the front half, what's happening to the value of the derivative? It's getting lower. Would everybody agree that the value of, if you were to consider the slope of the tangent lines, it's getting less? It's going from positive to negative. It is decreasing in value. Okay. Then, at this spot to this spot, what's happening to the derivative? Right here, it's negative. Is it more negative or less negative? Less negative. How about here? Less negative. How about here? So what's happening? So you said that over the course of this part here, that the derivative was decreasing, right? The rate of the change of the derivative was negative. That the values of the slope lines were becoming less and less and less, right? What's happening here to those slope lines? They're increasing. This is what we call concavity. Concavity is if the second derivative is decreasing, it's concave down. If the second derivative is positive, it's concave up. You could think of it like this, okay? If I were to dump water onto the graph, would this part shed the water or hold the water? Shed the water. We say that's concave down. Would this part of the graph shed the water or hold the water? That would be concave up. So, concavity is defined this way. Concave up if f double prime of x is greater than 0. Concave down if f double prime of x is less than 0. The inflection point occurs. What is the inflection point? The inflection point is where it changes from one to the other. Inflection is where concavity changes. Or f double prime of x changes from positive to negative, or f double prime of x changes from negative to positive. That's an inflection point. Second derivative test tells us about concavity and inflection. First derivative test tells us about increasing and decreasing, local max and local min. Now, last thing, local max or local min? Local max right here, right? Everybody good with that? Is it concave up or concave down? Concave down. So you can tell if something's a local max by looking for where f prime of x is equal to 0. So if you find that the first derivative is equal to 0 and f double prime of x is less than 0. If you have a derivative that's equal to 0 and the second derivative is less than 0, meaning it's negative, that you're going to have a local max. Local min, if f prime of x is equal to 0, but f double prime of x is greater than 0, that means it's concave up. That's going to be a local minimum. It's concave up. It's going to have a low part to it, okay? That's really not that crucial. We'll refer to it later on. That's the substance of what we want to do. Are you ready to apply it to a problem? Here we go. Flip it over. For the following functions, identify intervals of increasing, decreasing, concave up, concave down. Also identify local max, min, and inflection points. So here we are. Increasing, decreasing, max, min, concave up, concave down, inflection. Are you ready? Here is the function. F of x is 1/3 x cubed minus 4x plus 2. The question is, where's the function increasing, decreasing, concave up, concave down, local max, local min, inflection? Turns out we need to check out the first derivative. Somebody tell me the first derivative of this function. X squared minus 4. In order to determine concavity, I must consider the second derivative. Somebody tell me a second derivative. 2x. Sweet. You have two options to be able to consider these functions. Two options. You can either look at the graph or you can interval test. I would encourage you to always look at the graph if possible. Do you know what the graph of f prime of x looks like? I hope you do. Goes through -2, +2, and what shape does it make? Parabola. Awesome. This now tells me a ton of information. And nothing we did yet was complicated, was it? So this is where you need to decide, what does that tell us about increasing? Without looking at the first page, what is the definition of increasing? F prime of x is greater than 0, or f prime of x is positive. This is f prime of x. Where is it positive? Is it positive here or negative? It's positive. Is f prime of x positive or negative here? Negative. Positive. F prime of x is positive wherever f prime of x is above the x-axis. You're not looking, remember, this is f prime of x. Now, to get to Dylan's point, I point here and Dylan said negative. The second derivative is negative here, but f prime of x is positive at that spot because it's above the x-axis. Everybody good? So therefore, where is it increasing? It's increasing from negative infinity to -2, union with 2 to infinity. Well, that wasn't that bad, was it? Where is it decreasing? We do not include -2 and 2 because at that spot the derivative is equal to 0. It's not increasing or decreasing. What is the definition of a local maximum? Think about the local maximum. What happens at that spot? F prime of x changes from positive to negative. You're right, the derivative will be equal to 0 at that spot, but we have to consider where it changes from positive to negative. Where does this change from positive to negative? This is where I change from positive to negative. So therefore, it's going to have a local max at -2. Where do I have a local min? What's the definition of a local min? Where do I change from negative to positive? 2. Yeah. If you think about a maximum occurs where the derivative changes from positive to negative. This is the derivative. So it changes from positive above the x-axis to negative below the x-axis at -2. A local minimum occurs where the derivative changes from negative to positive. And because this thing is the derivative, it goes from negative below the x-axis to positive above the x-axis at 2. A little bit better? Okay. Folks, if that part's confusing to you at all, that's not abnormal. It takes a while to understand, am I looking at f of x or f prime of x? This is f of x. This is f prime of x. And it's confusing as you consider those pieces. This might help. Do you know what the graph of 2x looks like? What does it look like? Yeah. What's the definition for concave up? F double prime is greater than 0. This is f double prime. Where is f double prime greater than 0? From 0 to infinity. Where is f double prime negative? Inflection occurs where F double prime changes sign. Where does F double prime change sign? Inflection is going to happen where F double prime changes from positive to negative or negative to positive. So where does F double prime change sign? Happens right at 0. Exactly. Okay, so Grace is picking up on something here. It looks like concavity from concave up to concave down. You see a division at 0. It should be x equals 0 then. We good? It's negative infinity, negative 2 because as we consider, so first of all, let me help out this way. If you were to think of the original graph, if we were to look at that graph right there, that graph looks like this, okay? Looks something like that. And this spot of the graph is negative 2, and this spot of the graph is positive 2. So where it says increasing, you can see from negative infinity all the way to negative 2, it's on its way up. Now, we can tell that by looking at the derivative because we say, where is the derivative above the x-axis? Well, it's above here, everywhere from negative 2 on back. We're trying to put these two together. You are not looking at that graph. You're looking at this guy. But this guy is telling us about that one. Is that better? Okay. Good question. All right, let's try a second one. Okay. Increasing, decreasing. Max, min. Concave up, concave down. Inflection. You can always graph these on your calculator and see if you're doing them correctly as well. Okay. All right, I want to know about increasing, decreasing, max, and min. What do I have to look at? F prime of x. What's F prime of x? Sweet. Do you know what that graph looks like? We're going to test you on it. I'm going to factor out a negative 4x. If I factor out a negative 4x, I'm left with x squared minus 1. Does that factor? Like a negative 4x times x minus 1 times x plus 1. So fortunately, I had a really good college algebra teacher, and in chapter 3, he taught me how to graph polynomials. What degree is this polynomial? Third degree. Does it end down or does it end up? Ends down because it's negative. So since it's odd, it will start and end in opposite directions. It's going to travel through negative 1, 0, and 1. Sketch of the graph is going to make it really easy for me to determine these important pieces. I have to ask myself, where is it increasing? Where is f of x increasing? F of x is increasing wherever f prime is what? Positive. Where's f prime positive? That's where it's above the x-axis, so that's where the original function is increasing. The original function will be decreasing wherever the first derivative is negative or wherever the graph is below the x-axis, which would be from? How in the heck do I determine a local max? Yep, so every time I think about that, I picture a local max. I think about, okay, I'm going from positive to negative. That's what I think about every time, going from positive to negative. Where does it go from positive to negative? Negative 1 and 1. Where's the local min occur? Where it changes from? Where does it change from negative to positive? 0. Uh-oh, concavity. What tells me about concavity? Second derivative. Well, I haven't found the second derivative yet. Do we know how to find a second derivative? Well, yeah, we're really smart. F double prime of x is do you know what that graph looks like? Yeah, it's a parabola. It's upside down, right? Shifted up 4 units. Sure would be nice to know where it crosses the x-axis, though, right? Could we find that? Yeah, or we could just solve. I'm going to use a little scratch space here. We got negative 12x squared plus 4 is equal to 0. So 4 is equal to 12x squared. Divide by 12. 1/3 is equal to x squared. Square root. Plus or minus root of 3 over 3. Which, remember from last year, was the tangent of 60 degrees. Or the tangent of pi over 3. Should we write our answer like that? So that would be impressive. So you get to the AP exam, and instead of writing square root of 3 over 3, you leave your answer as tangent, plus or minus tangent pi over 3. Technically, they're the same values, and they would... No, I'm sorry, it's the tangent of 30 degrees. Oh, wow, somebody just called me an idiot, so pi over 6. But if you did that, they would have to give you full credit. Yeah, on the AP exam, you don't have to like simplify your answer. So you don't have to take 1 over root of 2 and write as root of 2 over 2. So as long as it is numerically correct, it's the right answer. So you could get tricky and show them that. And if they mark it wrong, then you could protest and say, change my score, it's right. Yeah, and then they would maybe write like a newspaper article about you and how smart you are and how you trick people. No, you wouldn't. What about Dylan's basketball shoes? Dylan. You are getting the group in trouble. Joke's on you. All right, here we go. So concave up wherever it is above the x-axis, which is going to be from negative root of 3 over 3 to positive root of 3 over 3. Yo. Go ahead. Free country. Negative infinity to negative root of 3 over 3. Union with root of 3 over 3 to infinity. Yeah, concave up is wherever the second derivative is positive. Second derivative is positive wherever the graph is above the x-axis. Where's the inflection point? Where's the change? The inflection point occurs when the second derivative changes sign. It changes sign right here. It changes sign right there. Changes from negative to positive, changes from positive to negative. Better? Okay, I'm going to pause it. I'm going to give you your assignment. The assignment so this lesson takes 2 days. So we're going to be able to finish it tomorrow. But we are going to do example C before the hour is over. But I'm going to give you guys about 5 minutes to work through the first example, start getting it in your brain. Okay, so we're going to take a break. You're going to start working. All right, Grant and Avery and Gigi and all you optional Wednesday people. We're going to pick up with example C. This is the last one we're going to do for the day. We'll pick up tomorrow. And we have 9x over x squared plus 1. Now, this is a little bit different. Why is this a little bit more difficult? You have a rational function. We still want to find increasing, decreasing, local max, local min, concave up, concave down, and inflection. I first want to start off by identifying the domain of this function. If you remember from last year, we could determine domain by looking at the top and the bottom. If I just had 9x, is there anything that restricts you from plugging something into 9x? You can have 0 on the top, that's fine. Can you ever produce 0 in the denominator? No, x squared plus 1 will never produce 0 in the denominator. So the domain is all real numbers. There's nowhere where this function is undefined. But I still have to take the derivative. How do I find the derivative of this function? Quotient rule. No easy way around it, okay? I'm going to use this space over here, but we will be doing this problem tomorrow, okay? So you might want to try to fit it in here. With my marker, I'm not going to be able to make that space work. So derivative of the top is 9 times x squared plus 1 minus derivative of the bottom, 2x times 9x, all over x squared plus 1 quantity squared. We good? What does the top simplify to? Yeah, so you got this negative 18x squared, positive 9x squared. You're going to get 9 minus 9x squared over x squared plus 1 quantity squared. Yep, 9 times x squared is 9x squared. This is negative 18x squared. Combined together, you get the negative 9x squared. This gives me a positive 9. We all good to go? Okay, so what we have to do is we got to do some interval testing here, okay? We got to consider where the top is equal to 0, where the bottom is equal to 0. So does the top factor? Factors to what? Yeah. Now, I know you don't know what that graph looks like, but tell me something about the bottom. Not only can it not equal 0, it's always positive. Does everybody see that the bottom is always positive? So therefore, if we want to know where it's positive, we just have to consider the top. Do you agree if the top is positive, the whole thing is positive? Do you agree if the top is negative, the whole thing's negative? So I know what that top looks like. Even though the whole graph doesn't look like this, the top looks like a function of a parabola that's upside down that goes through negative 1 and positive 1. So somebody tell me, where is this function increasing? That's where its derivative is above the x-axis. Somebody tell me where this is. Because it's 9 minus 9x squared. Decreasing. Union with. Awesome. How do I determine a local max? Where does it change from positive to negative? X equals 1. Now, I'm going to do something different this time. I'm not going to just find that it happens at x equals 1. I'm going to actually find the maximum value that it achieves. If I want to find the maximum value, what do I do with that 1? Plug it in where? To the original. And that would tell me the actual location of the maximum. I would get 9 over 2. Because what I'm going to do is I'm going to extend just a little bit further. I'm actually going to draw a picture of this graph. So I don't want to just know that the maximum occurs at x equals 1. I want to know the y value. I want to know how high to draw that maximum. So for example, if I draw a cubic, you could draw it like that, or you could draw it like that, right? Well, how high or low should I draw the max or min? Well, I just found. I draw it to a height of 9/2. This tells me the height, original function. I plugged in 1. 9 times 1 is 1, and then 1 plus 1 is 2. Yes. Because I want to draw a perfect graph. But you're going to on your assignment. The max occurs where you go from positive to negative, and the graph goes from positive to negative. The local min is going to occur at, if I plug in -1, I get a -9 up top. What do you get in the bottom? 2. So we get -9x. Okay? Shoot, I got to find a second derivative, don't I? So it looks like f prime of x was equal to 9 minus 9x squared and over x squared plus 1 quantity squared. What rule do I have to use in order to find that derivative? Quotient rule again. What's the derivative of the top? Negative 18x times the bottom, x squared plus 1, quantity squared. Minus, I'm just going to write the top, 9 minus 9x squared, times the derivative of the bottom. What rule do you have to use to find the derivative of the bottom? Chain rule. I'm going to have to make some more room for that. Use this space here. Let's see, we got u squared and x squared plus 1. Derivative of x squared plus 1 and derivative of u squared. So it looks like when I multiply these together, I get 4x times x squared plus 1, right? 4x times x squared plus 1. All over what? To the 4th power. That looks disgusting. What cancels? Nope. X squared plus 1. One of them will cancel, right? Like this has an x squared plus 1, this has an x squared plus 1, and this has 4 of the x squared plus 1s, right? So I could get rid of this one. I could reduce this to 1. I could reduce this to 3. So if we were to factor one of the x squared plus 1s out, it would cancel with 1 on the bottom, right? There will be 1 left here yet. Let's join some terms that are in the numerator. Negative 18x times x squared. Ooh, we pause there, folks. We pause there for the growl. We'll take care of that tomorrow. We'll finish this thing off.